Okay, good. Okay, good morning, everyone. My name is Stef. I'm a postdoc in Delaware, and I will talk today about a muon measurement from IceCube, more specifically about the high energy muon component we can measure in air showers in coincidence with IceTop and IceCube. So, um, let's see. The IceCube Neutrino Observatory, of course, while originally designed to study astrophysical neutrinos, is also a very powerful cosmic ray detector, as is demonstrated in this picture here. So on top we have IceTop, which is a 1 square kilometer array of ice Cherenkov tanks, elevated almost 3 kilometers above sea level. Then 1.5 kilometers below that we have IceCube, instrumenting a volume of about 1 cubic kilometer with about 5,000 digital optical modules. And combined, as I said, they make a unique air shower detector in the primary energy range of like PeV up to EeV, where we can measure not only as with the typical surface detector, the electromagnetic and low energy, mainly GeV muon component of air showers, but also we can measure muons which have energies of several hundred GeV, which can propagate here through the ice and leave a signal in IceCube. And it's these muons that will be the topic of my talk, and I will collectively refer to them as TeV muons. So, of course, we are interested in muons because they contain information about the mass composition and the hadronic interactions in the cascade. And it's of interest to do a variety of muon measurements because we know there is this muon puzzle, which manifests as a deficit of simulated muons at ultra-high energies, not necessarily at isotope energies, as you will see later. And this is mainly from GeV muon measurements we see this. So with IceCube, we can provide kind of a unique input to this problem. Namely, we can observe muons in different kinematic regimes. And in this work, we will determine the average number of muons with energies higher than 500 GeV in vertical showers. And so these muons are of special interest because they are created in the early stages of the shower. And model predictions for this observable are shown here. So on the vertical axis, this is the multiplicity of these high energy muons. And then this is our energy range here. That's 2.5 PeV to 100 PeV. And so we have here predictions for proton and iron for 3 different models. I note that Sybil 2.3 is not in there yet. That is, of course, something we plan to do in the future. A typical event that we use in this analysis is shown here. So we have signals in IceTop, which we use to do an air shower reconstruction. This gives us the core position, the direction, and the shower size, S125. And then if we have here this muon bundle signal, in coincidence, we perform an energy loss reconstruction here of this muon bundle in segments of 20 meters along this track. And then we select events which have their core contained inside of IceTop, which have successful reconstructions in both detectors. And we limit the zenith angle to very vertical showers with cosine zenith larger than 0.95 or a zenith angle smaller than 18 degrees. And so a neural network is then used for these events estimate the primary cosmic ray energy and the number of muons above 500 GeV in the shower. The inputs to the neural network are from IceTop, the shower size and the zenith angle, and from IceCube, the energy loss of the muon bundle. This neural net is trained on Sybil 2.1 with 4 primaries, proton, helium, oxygen, and iron. And in the plots here, we see the correlation between the reconstruction on the vertical axis and the Monte Carlo truth on the horizontal axis. In the top plot for energy, primary energy, and in the bottom plot for the muon number. Note that these histograms combine all 4 elements, and there are some small mass dependence there in the accuracy, which is not visible here. However, the accuracy of the reconstruction of the average muon number in bins of energy is shown in this plot here on Monte Carlo. So the reconstructions are shown by the crosses and the Monte Carlo truth is shown by the lines. And we see that the energy dependence is generally captured well as the difference between the primaries. However, there are some systematic biases left, and these are shown as shown in the bottom plot, which show the ratio of the reconstructed and the true from the top plot. And so we see biases there in our result that are energy dependent and mass dependent, and they are up to maximum plus minus 15%. And so to deal with this in the later in the analysis, we fit these ratios here with quadratic functions, and we will use them as multiplicative correction factors. Now, of course, a complication is that clearly the correction that needs to be applied is dependent on the composition, and we don't know the composition. But rather than assuming a specific model, we deal with this with this iterative method, where we use, well, two important facts. One, our muon measurement itself is a measure of composition, and two, the correction factors, as we saw on the last slide, very smoothly with LNA. And so what we do is we get an estimate from our for our muon measurement from our neural network, compare this to proton and iron simulation to get a estimate of the composition, and then we use this composition estimate to interpolate the correction factors between proton and iron, apply this to get a corrected estimate of our muon multiplicity, and then we iterate this procedure until we find converging values. And this plot here shows an example on Monte Carlo that was weighted according to the H4A model. This is what the composition looks like. And we see here that the blue points, which is the muon number in this Z scale, after several steps of the iteration, they line up with the orange points, which are the Monte Carlo truth. And so we've tested this for a very large number of possible mass compositions, and we find that this method reproduces the true multiplicity well, regardless of the true composition. And so here are just 4 examples of a pure proton, pure helium, oxygen, and iron case. And any kind of small remaining differences we include as a systematic uncertainty in the final result. So now that we have this analysis set up, we can apply it to experimental data, and we use here 1 year of data, where the snow coverage on top of IceTop agrees well with the simulations we've used for training. And we see here in the bottom plot the average muon multiplicity we get as a function of energy, and this goes from several tens of muons at 2.5 PeV up to several hundreds of muons at 100 PeV. The numbers here are just the number of events that contribute to each energy bin. And then on the right plot, we show the systematic uncertainties, and this is the snow coverage on top of IceTop contributes to this, the calibration of the charge unit in IceTop, and then there's the big one is the in-ice light yield, so that the IceCube ice model, as well as the efficiency uncertainty of the DOMs. And so the total systematic uncertainty here related to the detector is about 18%. Now, clearly, the results here are model dependent. Everything we've done so far is based on Sybil 2.1. We can also derive results based on other hadronic models. And we do this by deriving correction factors based on Monte Carlo from, that we run with QGSJ 204 and EPOS LHC. And you can see these different pairs of correction factors here. And then applying these correction factors to our data, we find the following results. So here we see the mean multiplicity of muons with energies above 500 GeV in our near vertical showers as a function of primary energy. The shaded area here gives the total systematic uncertainty. And each result here is compared to proton and iron expectations from the corresponding model, of course. And what we see in each case here is that the nominal result is nicely in between proton and iron. Now, of course, we can see more detail if we plot these in the so-called Z scale. So what we do is take the logarithm of the muon number and scale it in this way with proton and iron simulation, so that pure proton is at 0 and iron is at 1. And then we get these results here. Systematics are now shown by the brackets. And we also plot the expectations from the flux models H3A, GSD, and GSF. And what we see is that these high energy muon results line up very well actually with the expectations from these models, with EPOS LHC just indicating a slightly heavier mass composition than the other two we consider. So these are the results from the TeV muon analysis. As I said in the beginning of the talk, IceCube is unique in the fact that it can also measure the low energy muons with just a surface detector. And so it's of interest to compare these results. And so we'll briefly introduce this analysis again. Matthias mentioned it yesterday in his analysis, but this is an IceTop alone muon density analysis described in this paper here. And in this analysis, we derive the density of muons at 600 and 800 meters from the shower axis. And we do this by making this charge versus distance histogram, and then using this muon feature here at large distances to derive the muon density. And so we can do this by taking vertical slices here, fitting this muon peak, and from this extracting the muon density as a function of energy. And so here's an example result for Sybil 2.1. We have these two different distances. And we can compare the results from this analysis, this GeV muon analysis, to the high energy muon analysis that I've just described before. And so a comparison is shown here. In black, we see the results from the high energy muon analysis. In orange, the different shades, we see the results from the IceTop alone GeV muon density analysis. Now, of course, we expect the two to be compatible with each other within systematic uncertainties as they relate to the same underlying mass composition. And we see this as the case here for Sybil 2.1. The black points for the TeV muons align well with the orange points for the GeV muons. But we see there's somewhat of a tension when looking at QGH and EPOS, where the low energy muons indicate a significantly lighter composition. So showing that there's probably some discrepancy here in the description of reality. I note that there was a comment yesterday during Matthias's talk that you could fix the low energy muons here in IceTop by shifting IceTop's energy scale, and then these muons shift up to line up somewhere here in the middle. But we can see now that if we do this at the same time, we will mess up the high energy muons. So there's really some kind of issue here that cannot be attributed to a simple energy scale offset. So that brings me actually to my summary. So I've presented here a new analysis of the mean number of muons with energies higher than 500 GeV in near vertical air showers. We find that these results are in line with expectation from simulations. However, when comparing to the GeV muon measurement performed with IceTop alone, we find a tension in QGSjet and EPOS LHC, which may indicate that there are actually too many low energy muons in post LHC models in our energy range, at least at these large lateral distances that we are looking at. And so this is an opposite effect of what we see at ultra high energies. I want to point out also that we don't want to claim here that Sybil 2.1 does not have its problems. We have more preliminary results where we see also inconsistencies there when looking at the slope of the LDF we see in IceTop. So for anyone interested, we have plots in the backup there. Then looking forward, there's a paper in progress describing this muon analysis, high energy muon analysis, including this comparison with a bunch of more checks related to energy reconstruction and so on. And of course, with IceCube, we want to continue doing this type of analysis to provide more constraints on hadronic models. We're working on improved analysis with improved systematics, and of course, we will have new detectors in the future, which will allow us to do more new things as well. And yeah, with that, I will end my presentation and take your questions. Thank you.
Okay. Thank you very much for the interesting talk and for staying well in time. So you probably risk your coffee break. So questions there was Kevin, Ralph.
Thanks, Stef, for the presentation. I have a couple of questions. Do you have a feeling about how Sybil 2.3D might change those results? And if you have also maybe a time frame to give us on when this will be implemented. And the second question is KM3net release. I talked to you about it earlier, but maybe you can comment here as well. Reported on also a muon excess in TeV muons, but I think at lower energies than what you're looking at. Is there any chance that with IceTop you could also reach these lower energies like TeV energies to see those TeV muons?
So to the first question, let me see. Yeah, I don't have the actual predictions for Sybil 2.3, but from what I've seen from, for example, the Sybil 2.3D paper, I feel like the high energy muons are fairly similar between these models. So I don't think there will be too much big changes there. Then for the KM3net question, yeah, I'm not sure. I mean, it's a different type of analysis, right? They look at an inclusive flux. Here we tag air showers with the surface detector, so I'm not sure how comparable they are. I think with IceCube alone, you can probably do a similar analysis, and this is probably something we should think about doing. Yeah.
Thank you. So yeah, it's what you said is also interesting that if you change the energy scale, you change for both. Yeah, but I still have a problem that Sybil does not reproduce LHC data. I mean, Sibyl, we have very large problems. So if your data is well reproduced by a model which doesn't reproduce collider data, that's another problem. Huh? So
Yeah. So I did mention there are problems in Civil. Let me go to the backup. This is a plot we have also from Civil 2.1 where we have one more observable. It's a bit more preliminary, which is why I didn't put it in the main body, but this is the kind of the slope of the LDF we see, which is some complex combination of electromagnetic and muons. And we're trying to improve this to kind of disentangle both effects and see what's going on there. So it definitely also has its issues. And then these do improve in these other two models.
I'm looking forward for CB 2.3D to see, yeah.
I think we have some online questions I would take, and then I continue in the room. If you don't mind, Chris.
Hello, Professor. May I audible to you?
Mm-hmm.
I have a question.
Yeah. Go ahead.
You said muon bundles observed in IceCube experiment. That means parallel muons bundle.
Sorry, what was the question? Get it.
You said muon bundles observed in IceCube experiment. It is parallel muons.
Oh yeah, so we are not able to disentangle the individual muons. So let's see if I have the event display here. Yeah, this would be a bundle of tens to hundreds of muons
Because
show up as one blob of fairly parallel muons in a detector.
Because in Kolar goldfields at 2.0 kilometers deep underground during 1999 in proton decay experiment, we observed around 20 parallel muons bundle. It was under Indo-Japanese collaboration experiment.
Yeah, I think these muons are fairly parallel. We have also an analysis that looks for laterally separated ones with like high PT muons.
Yes, very well separated ones. Yeah.
Yeah. And so the scale here is like, you know, the detector has a rate or has a diameter of about 1 kilometer. So it's a pretty collimated bundle.
Okay, thank you, Professor.
Ralph?
So I think that's really one of the analysis that is at the heart of this meeting here, what you show. And what we knew from the beginning that the 500 GeV muons are basically more or less the same in the different models, which is maybe by accident, but maybe it tells us more about how well we can predict them. But the GeV muons, of course, at larger distance, we have a much harder time to predict. So in this sense, what you see here, probably your data we can use as an anchor point and work on the models without having this very cumbersome and time-consuming simulation chain, because we know then in principle the muon number and we can sort of maybe simplify things. That I hope is a way that we learn from it. The other thing is I would like to see a correlation one-to-one between events with lots of muons in ice and in IceTop. Can't you make such a correlation plot, or is your neural network thing not giving you an estimate event by event?
We can definitely do it for this high energy muon analysis. The problem is that the low energy muon analysis is a statistical one, so you need a large amount of events. I have been thinking about just making a sample of, or doing a selection first on high multiplicity bundles in ice, and then running the muon analysis on that sample, and then splitting it up into two, for example. But
it would be nice to see how much of a spread one really has, how much this is correlated.
Yeah, I agree.
Because I think we are going to learn in addition. And then the other, just to comment on the KM3net, the KM3net analysis, because it's inclusive flux, you basically see the first interaction. It's really the first interaction that they measure the muons from, or just to a large degree, maybe a second one too. Whereas here you see all the chain down to the muons, which is to the GeV muons, it's probably 10 generations. Yeah. So it's really a different, or it's a complementary measurement. And so in this sense, we really learn from the two in a very independent way. Yeah.
Yeah. Also, the primary energy range is very different. For KM3, it will be 10 TeV.
Yeah.
Column rate. Yeah. Oh yeah, maybe also worth mentioning, people are working on event-by-event estimators for the low-energy muons. So we hope to do that at some point.
Okay, first of all, very elegant analysis. Good to see clear-cut correlation. My question was also very similar to what actually Ralph made point, that you have these very systematic differences. So is it because the low energy interactions are far more complex and difficult to comprehend that you are seeing differences between models? So maybe this experiment can be used as a laboratory to maybe tune the models. So I had a very similar come.
Yeah, I don't think I can comment on the modeling, but I hope this kind of measurement can be useful indeed. Yeah.
Okay. So I think we should move on. Thank you again for the interesting talk, and